So when we talk about different types of functions, we're also going to be talking about the models that go along with them. All right. Sometimes functions and models are used sort of synonymously, as if they're the same thing. In some cases they are, but basically if you think of a model as a function with context, then you're starting to get in the right direction, right? So just a quick refresher on functions. If you're thinking about them graphically, very simple. It's a graph that passes the vertical line test. I almost wrote vertical line list for some reason, I don't know. Graph that passes the vertical line test. Now, that's very simple if you know what the vertical line test is. If you don't, then oh, well, now, unfortunately, you're not going to pass the course. No, let me just show you really quickly. I like to, you'll see before too long that I really like Desmos, and I like to illustrate wherever possible. I think people like me who can't draw really gravitate towards technology that'll do the drawing for me, because it can actually get the ideas that are in my brain out onto paper for the world to see. So let me see, y equals, we'll go with something straightforward like x squared. All right, nice parabola for you. Now let me get a vertical line in here. I'll call it x equals a. Because what I was showing you before is if I use a constant value, right? If I use a constant, oh, that's so strange. That, I wasn't ready for that. Let me try x equals c. Oh, you know what? Okay, I know what I'll do. I'll just type in x equals 0. And I'll make it go well. Okay. All right, so I got a nice little movable vertical line here. I actually forgot there for a second that if you just type in x equals a number, it automatically creates a slider for you. You don't need to do a constant like I did before. But you see here, I have it going back and forth, sliding back and forth. And you'll see that in each instance, that vertical line only intersects with the parabola just once, all right? So anytime you pass a vertical line through another graph so that it only intersects with that graph once, or maybe not at all, but no more than once, then it passes the vertical line test. So this parabola is a function, right? But let me show you a different one real quick. Plus y squared equals 4. All right, and so for this one, the circle, you can see here that we have multiple intersections on the circle. As I cut through it with a line, you know, the line is the hot knife, and the function is the butter, I guess. It's probably not the best example because this doesn't have any substance to it. It's just the circumference of the circle. But we can see here that this line is only intersecting that circle, well, only twice, but it's still too much. Right? There are some instances where it only intersects once, and it's like, oh, so it's a function. No, because it intersects more than once over here. Even though it's only twice, it's still not going to be a function. All right. Now, if you get something, you know, really kind of crazy, let me see if I can. This I'm not sure if Desmos will do, but I'll try it. X equals. Yeah, there we go. Do a sideways trig function. You can see here that you'd have infinitely many intersections. Now, again, there's some instances where you only have, where you have no intersection. like over here and over here. But once you hit the curve, now you have multiple intersections. All right. So this would fail the vertical line test also. Right. So that's what I mean when I talk about a function in terms of the graph. But when we talk about a function in context, that's what a model is. Right. So it's a function in context. And right now, somebody's got to be thinking, man, this course is going to take forever. We're like 10 minutes into this video and he's still talking about the title. It's that important.
No,
and I promise
this really helps. Like
it
seeing
does.
things. No other teacher's done this, so I really appreciate this. Thank you.
Yeah, no problem. I'm happy to do it.
I hope you keep doing this with everything because it clears up a lot of confusion.
That's the whole idea, because you know what, I meant this when I said it last class, that your strength in pre-calc is going to dictate your performance in calculus. So to gloss over anything in this course is just terrible, you know. So yeah, so if you find it helpful, that's great. If you find that I'm doing something that's not very helpful, let me know that too. Just nicely.
Do you mind if I ask you, are you as a teacher like supposed to teach a certain amount of this course? Because I feel that other professors have rushed this on purpose because they're trying to squeeze in X amount into a course. Do you understand what I'm saying?
Oh yeah, yeah. We have a curriculum and we have to get through the curriculum, and we always do. Yeah, I don't know what approach they're taking that keeps them from being able to get through the curriculum, but it's not, whatever it is, it ain't good, because there is opportunities to focus on the fine details while also not falling behind.
Okay, so it's on them. It's not on.
It's
not on the school pushing. Yeah. Okay. I was just curious.
Yeah, it's never the school. I wish we could do it. So yeah, so function in context, and so what we think about when we talk about something being in context is you might get into, you know, like that shivery feeling of dread when you start realizing that context usually means word problems, right? And so that's really the name of the game, because in a lot of cases it's like, why learn this if you're not going to use it for something, right? So that's what the modeling is going to do for us. It's going to show us some of the applications of these functions, right? Honestly, I could be completely transparent about this. I'm 22 years into my career right now. So I'm on like back 9 at this point. But when I was about 10 years in, so it's only like half a career ago, I didn't really have an intuitive understanding of why functions were important. Like it always seemed like every course I was teaching, we would start off with a discussion of the vertical line test. It was, this dang vertical line test. Why do we always have to talk about it? I didn't realize just how important it was until, of all things, I was watching a Mets game. And you wouldn't think in a Mets broadcast it would matter for anything. Yeah, no, I lost like half of the class with that one. Just like Mets. Yeah. Oh no. No, we were doing so well.
I'm a Yankees fan.
Yeah. I think they play each other next week. Nah, it's all right. I'm one of those people that love the Mets, and in my mind, the Yankees are just irrelevant. So I don't have a hatred for the Yankees like most Met fans. They love the Mets and they hate the Yankees. I love the Mets and I don't care about them. I hate the Phillies. Like if you could take a team and just remove it from Earth, and you like
Boston.
Send it off into a, yeah, exactly. Yankee fan, know that feeling. Yeah, just put them in a rocket ship and send them somewhere and like never hear from them again. That would be Phillies for me. That would be Red Sox for Yankee fans. But yeah, I was watching this broadcast, and the general manager, he made a comment, and you know, I think I've heard this comment so frequently, but for whatever reason, I was in tune with what he was saying. And he said that the team's performance is a function of their pitching. And I was like, and I started thinking about it. It's like the weirdest thing to be thinking about. And honestly, if you ever watch baseball, you do have time to think, because there's a lot of time in between action, different plays that occur. And I remember thinking, what on earth does he mean by that? And then it didn't take too long before I realized he was saying, in context, in just the intuition of it was, well, if the pitchers do well, they will win. If the pitchers do not do well, they will lose. And I thought to myself, I'm like, okay, so he used the word function, but I use the word function. I wonder if we mean the same thing. So a function is about being predictable, right? In order to determine something is a function, you would use a vertical line test, but that's only a small piece of it. The major component of it is that if you have an input, you will have a predictable output, no more than one output for that input, all right? So you start building arguments like, if this, then that. It's conditional, right? If the Mets pitching the pitching staff does well, then they will win. It wouldn't make sense for me to say, well, if the Mets pitching staff does well, the Mets are either going to win or lose. Well, then the performance of the pitching staff is irrelevant. It's kind of like, if I took this vaccine, I will either be safe from the virus or prone to the virus. It's like, well, what did you tell me to entice me to take that vaccine? But if you say, if you take this vaccine, you will be protected from the virus as a condition. If you do not, you will not. Now you're talking about a function, right? Some things don't really lend themselves to functions. And I think about things like, or at least not in a very cut and dried sort of way, more of an intuitive way. But if you think about it, like, if you have a lot of weight in your car, like you have a gas, combustion engine, and you have the trunk filled, you have the back seats filled, everything is filled with like bricks, it will impact your gas mileage, but it won't necessarily pin down at a particular number. But you can make a conclusion from that by saying, if I have more weight in my vehicle, my gas mileage will not be as good, right? It's the same idea. Those are the intuitive applications of functions. What we need to do is tackle the just cut and dried graphing, writing equations, things like that, before we can tackle the more interesting things. But those interesting things are really at the heart of the issue here, because they get us to understand why we're doing these things, right? And so what's going to happen is, you'll see invariably that sometimes a function will be linear and sometimes it'll be trigonometric, right? So just giving you a quick trigonometric here, y equals the sine of x. This function is known as a periodic function. It increases, decreases, infinitely. All right. So if you can think about a situation or a circumstance in real life that increases to a maximum, then decreases to a minimum, then increases back to a maximum, then you would have an idea of a good application of a trigonometric function. All right. The first one that pops to my mind is temperature throughout the year. All right. You get into July, you're at the high temperature. You get into December, January, February, you're at the low temperature. But at every other point, you're either increasing to the high temperature or decreasing to the low temperature, or increasing back, if you get into the next year, increasing back to the high temperature and low temperature and so on, in a cyclical pattern, right? The distance the Earth is away from the sun, phases of the moon, all periodic. Aside from the obvious things like wave height, like when you go to the beach and you see the waves coming in, those actually look like trig functions. Although you don't see the bottom all the time, you do see the top, right? So this should kind of give you a sense of what we're going to be looking at, not just the what and the how, but also the why. All right, I'm a big fan of the why. So the slope-intercept form. Slope-intercept form, very straightforward. This is the one that you're probably most familiar with, y equals mx plus b. And slope-intercept form of a linear function. All right, the m is the slope. And the b is the y-intercept. All right, you might see it in another form. Some calculators, textbooks use ax plus b instead of mx plus b. It really doesn't amount to too much of a difference. All right, the point slope form is y equals m times x minus x sub 1 plus y sub 1. All right, that's the ugliest one in appearance, but it's the most useful one. So you got to kind of come to grips with that piece of information. You're like, oh, this is great. The one I like the least is the one that I'm going to need to use the most. All right, well, isn't that how it always works in math, right? So the m is still the slope. x1 comma y1 is a point on the line. All right, it's some point on the line. It could be any point on the line. Doesn't matter what it is. That's the power of the point slope form. It could be a disgusting looking decimal, or it could be a nice round number like 0, 0. All right. The standard form, that even I have a hard time justifying the existence of this form in this class. I can tell you that as you go further down the line and start exploring other aspects of mathematics, like linear algebra, anything involving matrices, you start seeing the value of this form, which is known as the standard form. It actually, it's a different conversation, but it shouldn't even really be called the standard form. They just call it that in textbooks for some reason. But anyway, that's a different conversation. So what we would generally do is solve this one for y so that we could get it into the slope-intercept form. All right, so we'll just do that in general terms. So this is, again, the standard form, so I'll use my highlighter. I'm going to subtract an ax. That would give us by is equal to, I'm going to write it with the ax term first and then the c. All right, so negative ax, that c is an assumed positive because it had no numeric, no signage in front of it. It has some assumed numerical value. So ax plus c, and then I would just divide everything by b. So each term gets divided by b. All right. When you divide,
you always minus the ax. I'm sorry to interrupt you.
Yeah, no, it's totally fine. Yeah, you're always going to subtract the ax because we want to get the y alone. So we need to get rid of that term first.
Thank you.
No problem. So y is going to be equal to, I'm going to write this as negative a over b x plus c over b. All right. So the benefit of doing what we just did, you know, it's, you might look at it and say, well, I don't see any benefit whatsoever. It helps you to pull the slope and the y-intercept from the standard form, right? Because if we match this model up, this one here to this one here, it has the same form. So whatever is in front of the x, that's going to be the slope. So negative a over b. And the y-intercept is going to be c over b. All right, that's useful when it comes to finding rates of change for creating a graph. Now, there is an element where it'll seem like I'm kind of speaking out of both sides of my mouth, where I'll give you all these little tips and tricks to come up with a graph and then do it all on the calculator anyway. So you're like, well, what was that all about? It goes back to what I was talking about last class of, I don't know where you're going to be next semester. You know, you're in a class with a teacher that says you can't use a calculator, and you're like, now what? You know, so I give a little bit of something for everyone, or at least that's the hope anyway. All right, so the standard form is ax plus by equals c, knowing that the slope will be negative a divided by b, and the y-intercept will be c over b, will help you do other things. All right. So let me take you through an example. And this, let me see here. Yeah, these next two examples will be it for tonight. That I've already had, you know, kind of plowed through a lot, but I also want to stick to my 7:20-ish, 7:25 end of class time in case people have questions. Right. So the example: write the linear equation in slope-intercept standard and point slope form, given the line passes through 5,2 and 7,9. All right. So first I would compute the slope, which is change in y over change in x. The order doesn't matter as long as you're consistent. All right. So what I'm going to do is I'm going to take the 9 and subtract from it the 2. And then correspondingly, I'm going to take the 7 and subtract from it the 5. All right, because I started with the second coordinate, the 9, for the y's, I would start with the second coordinate, the 7 for the x's. All right, so 7 minus 5. All right, so that'll give you 7 halves. And I'll show you a Desmos way to do this in a couple of minutes. All right. So that's my slope. Now, I need to come up with each one of these forms. So I'm going to choose to come up with the point slope form first. All right. All right. So the point slope form only requires us to have the slope and a point on the line. All right. We have 2 points on the line. So I have one, I have 2 to choose from. I have an embarrassment of riches here. All right. So I have this coordinate here, or this ordered pair, that I'm going to call x1, y1. All right. I could have easily gone the other way. I could have called this one x1, y1. Doesn't make a difference. All right. So if I do that and I plug into this model here, a little extra E coming along for the ride there, get rid of that. I would replace the slope, the m, with a 7/2. The x1 gets replaced with a 5. And the y1 gets replaced with a 2. And that would be it. That's all I would need to do. All right. So you'll see in a couple of minutes after I go through the other cases that this should be your go-to. You should be pretty motivated to want to go this route, just because there's not a whole heck of a lot of work. That's assuming you have to do it by hand. All right, if you can use a calculator, which you will be able to use throughout this entire course with no restriction, then it's a different story. There's other techniques, but you know, you got to be prepared for the worst and hope for the best. So the next form that I'm going to go for here is the slope-intercept form. regardless of the method you choose, you're always going to have to figure out the slope first. So all of this had to happen no matter what. But what I can now do, because I've come up with the equation in point slope form, is I can work off of that. I can start with that, distribute the 7/2. So 7 halves x minus 35/2 plus another 2. And then simplify. You just got to take that negative 35/2 and add 2. You do that in a bunch of different ways. Yeah, if you want to go calculator, go calculator. Let me just show you really quickly on the calculator, only because there's nice features in Desmos that allow you to do this pretty easily, right? But if you want to get a common denominator, that 2 would become 4/2, negative 35 plus 4 is negative 31. You do that way, but let me show you on Desmos. So if I wanted to type in just this expression here, I don't need the x stuff because that's already simplified, just this piece. I would first type in my minus, then I would type in a division symbol to bring up a fraction bar. Then type in my 35/2, click or tap into the numerator to type in the 35, then click or tap into the denominator to type in the 2. Hit the right arrow or tap out of it in order to get to a separate expression. And then just, and you see it's already giving you a decimal, the decimal equivalent of this, which is nice. Then I would just type in the +2. Now I have a decimal answer. If you want the decimal answer, you could write that down. I have a general rule of thumb when it comes to decimals. They're perfectly fine as long as they're clean decimals, right? If they're ugly decimals, as in irrational or just unfriendly decimals, basically we're not looking for rounded answers, right? Unless it's a word problem, and in those cases, the word problem will dictate what the rounding should be. If it's a clean decimal, you can write it as a decimal, otherwise convert it into fraction form. Now, this one I know has a fractional equivalent available to it, because if you look at Desmos, you see a little blue strip on the left-hand side, it's got a fraction icon. That's telling us that if I tap on that or click on it, it'll convert it over into fraction form. All right. And there's, an obvious benefit to that, especially if you're looking at something that maybe you didn't think could be converted into a fraction. Now you look at it and say, oh, look at that. It's a fraction and I didn't even have to do any work. All right. So if you're ever in doubt, just think, what's the title of the course? Title of the course is not algebra. It's not computational skills. It's pre-calculus. It's a preparation for calculus. All right. At no point will I say that an algebraic solution is the only thing that I'll accept. I always accept multiple different techniques. Now, if this class were an algebra class, it'd be a different story, but it's not. So with that in mind, I can show you the graphical approach. Well, let me not steal my own thunder too much. Let me get through the standard form real quick, and then I'll show you the graphical approach. So for the standard form, it has to be in the form of ax plus by equals c. All right. All that means is that x and y have to be on the same side of the equation. So for that, I would take my answer from slope-intercept form. Now, because this is the negative 31/2, actually, I want to move the x. So let me not make this overly complicated. Because this is a positive 7/2, let me subtract off a 7/2x. That y is assumed to be a positive y. Put it all together, and you get negative 7/2x plus y is equal to negative 31 over 2. Now, if you want to clean it up, that would, by the way, that would be an appropriate standard form because x and y are on the same side of the equation. But if you wanted to clean it up, you could multiply everything by 2. You know, make it look a little nicer so it doesn't have denominators. That's perfectly fine. But a good way of verifying that you did it correctly is by taking the quote unquote A value. You get a little pink over here. The A value and the B value, the understood coefficient in front of y is a 1. That would be the B value. The slope should be equal to negative A over B. All right. So that would be, the negative is built into the formula. So negative 7 over 2 over 1 is 7 over 2. It's a nice, quick, easy check to make sure that you put it in the appropriate form, because that computation of slope should be equal to the same computation that we came up with earlier. All right. This step here, all this, that's not necessary for the solution. Your final answer is right here. If I can get a box out of this. But it's nice to know that you have a quick way to verify by hand if you needed to. All right. That being said, there's other ways to verify. And so we're not even going to bother with number 2. I'm just going to show you the graphical approach, and then we'll call it a night. But first thing I would do is type in my 2 coordinates, 5, 2, and 7, 9. Now this, what I'm about to show you, will help you to verify that you did the work right. Right. And so to do that, all you'd have to do is type in, you know, 1 or more of your final answers. I'll type in my point slope form here. Y equals fraction 7 over 2. X minus 5 in parentheses plus 2, and just make sure it goes through the 2 points. All right. If you do that, then you know you did it right. Okay. Now, if I want to get from here to the slope-intercept form, then I need, well, I already have the slope, but I would need the y-intercept. So what I can do is slide back, tap on the intersection between the graph and the y-axis, and whatever that y value is will be the y-intercept. So I already have the slope going in. Now I know the y-intercept. Algebraically, it's just a matter of moving a term over to the other side of the equation to get it into standard form, so then you'd be done. All right. So that's a nice, easy way of checking your work. But if you want a way to actually let Desmos do the work for you, then you would want to use what's known as a table approach. All right. So let me just bang this out for you real quick. I'm going to go over this again next class, just because with Desmos, it's an acquired taste. But I just wanted to expose you to it really quickly. So what you would do is create a table and type in your coordinates. So 5 for x1, 2 for y1. So that's x comma y. And then 7, 9 for the second order pair. All right. So what Desmos will do is it'll build an equation based off of whatever form you give it. All right. So what I would do here, if I want to do it graphically on Desmos, is I would first type in y1, and then I'm going to put in a tilde. All right. So I'm going to make a little note of this. So in Desmos, I'm going to essentially just put in my slope-intercept form, except I'm going to use tilde instead of equals, and x1, y1 instead of x and y. All right. If you type that in, it'll give you the equation of the line, right? So where do you get the tilde? You go into the ABC, you'll find it. It's in the bottom row, 2 to the left of the enter key. Tilde is Desmos speak for regresses to, or is modeled by. I mean, we'll get into that a little bit more down the line, but in case you were wondering. M, X, followed by a 1, it automatically makes it a subscript, plus B. All right, and so what it'll do is it'll fit a line to the points. That's where this line came from. But then it also tells you what M and B should be. M is in the slope and B is in the y-intercept. 3.5 for the slope, negative 15.5 for the y-intercept. 7 over 2 is 3.5. Negative 31 over 2 is 15.5. So right here, I can't really highlight that, but in this calculation here, where it says parameters, it'll then tell you what the M and B values are. So just by typing in this one little command, and I'll show you other types of functions for parabolas and trig functions, stuff like that. But by knowing the appropriate command in Desmos, you can get the equation without doing any of the algebra, right? So I know that was throwing a lot at you. I don't expect you to know it all in one night, but definitely take some time. And if you haven't created a Desmos account, do that. And next class, I'll start off going over this concept again. But I wanted to make sure I exposed you to it before we got too far underway. All right, so let me stop the recording.